No, let's start the recording. Yeah. Okay, so we are up and running again, back for another problem session. So I'm going to pick up where I left off last time, 5.2.13. So here we go. And I have some students in the room, so if we hear voices, those are hopefully student voices and you're not hearing voices. Anyway, so we are asked to perform Gram-Schmidt on 3 given vectors. So they all live in R4. So that's V1, we have V2, 1, 0, 0, 1, and V3, which is 0, 2, 1, minus 1. So we are going to find the 3 orthogonal vectors Q1, Q2, and Q3, and in the process we will also compute the QR factorization. So let's just set this up. So we're going to have the Q matrix, which will have 3 columns, 4 rows, and we'll have the R matrix, which will be 3 by 3. Yeah, and it's going to be upper triangular, so we have zeros here. Okay, so first step is to find the length of the given vector v1. All right, so we're of course measuring in the 2 norm, so it's 1 squared plus 1 squared plus 1 squared plus 1 squared and the square root of that. All right, so we have that the length is square root of 4, which is 2. All right, so whenever we compute a length, that is going to end up in the R matrix. Right, so this particular length goes up here. All right, so that's the R11 element. And our first Q vector is just the length, or 1 over the length of V1 times the vector V1. Right, so we're just dividing each element by half. Right, so far, so good. And let's just enter that here. Okay. Then the next thing we want to do is, so we're done with V1, right? We want to pick the next vector V2, and we want to figure out the piece of V2 which is perpendicular to V1 or equivalent to Q1, right? That is, we want V2 perpendicular, all right? So what that is, we take the vector itself, we subtract the action, right, of V2 in the direction of Q1. All right, so we project onto Q1. All right, so that means we have to compute this dot product. All right, so V2 dot Q1. All right, so V2 has ones in the first and last element. Right, so that means when we dot that with Q1, we multiply the half at the top and the bottom by 1, and then we add them. Right, so we should get 1. Right, so this element here will end up in our R matrix. Right, so dot products we compute along the way end up as superdiagonal elements. Right, so now we are in the first row, second column, so we get a 1 here. All right, so it's that 1 that ends up over there. Okay, then we can do this. So we have V2 being 1, 0, 0, 1. We're subtracting 1 times Q1, and Q1 is all the halves in here. right? So we end up in the vector that is 1/2 minus 1/2 minus 1/2 and 1/2, right? So that is V2 perpendicular, right? So what we want is we want to generate Q2, right? And what that is, it is 1 over the length of V2 perpendicular times V2 perpendicular, right? So we have to compute the length, right? So we need this quantity. So in this case, well, we can see that this length is 1, right? Because we have magnitude 1/2 in each one of the elements, just like we had for Q1, right? So indeed, it's 4 times 1/2 squared, right, for each element, and then the square of that. So it is 1. All right, so that makes our second diagonal element here 1, right? So it's that one that comes from over here. And then Q2 is just V2 perpendicular, right? So we can fill this in. So we have 1/2 minus 1/2 minus 1/2 and 1/2. Okay. So far so good. Let's clean up a little bit. So we're done with the first 2 vectors. So we're going to play the same game, right? So we pick the third vector, and we want to figure out what part of that vector is orthogonal to both Q1 and Q2. Okay, so that is, we want to figure out what V3 perpendicular is, right? So that is the original V3 vector, and then we're going to subtract whatever part of V3 is in the Q1 direction, right? So we project onto Q1, and then we subtract the action of V3 in the Q2 direction, right? So what that means is that we have to compute these 2 dot products, right? So what do we have? Let's start here. We have 0, right, from V3. We have the entries from Q1 sitting over here, so they're all 1/2. So we have plus 2 times 1/2 plus 1 times 1/2 minus 1 times 1/2. So that's that dot product. So that is 1, right? And my notes agree. So that 1 ends up over here, right? So dot products end up above the diagonal, right? So we have the third vector, V3, so we end up in the third column over here. We dotted with Q1, so we end up in the first row. Okay, so let's just say, so this was V3 dot Q1. So let's compute V3 dot Q2. So we have 1/2, or 0, right, from the vector. We multiply by 1/2 from Q2. 2 times, we now have a negative 1/2 plus 1 times negative 1/2 minus 1, right, from V3 times 1/2. So what do we have? We have minus 1 and minus 2 more halves. So this is negative 2. So that dot product ends up over here, right? So we have almost all of R. So then all we have to do is figure out what V3 perpendicular is. We have the original V3 vector, 0, 2, 1 minus 1. To that we are subtracting 1, right, that 1, times the Q1 vector, which had halves for all the elements. Then we are subtracting -2 times, right? We have a minus sign from the formula, we have a minus sign from the dot product. And then we have half, -1/2, -1/2, and 1/2. Right? So the two minus signs, of course, they make a +2 here. So let's see if we can get this right. So in the first component we have 0. We are subtracting 1/2, and then we're adding 2 times 1/2, so add 1. Then we have 2, subtract 1/2, add 2 times -1/2, so we're subtracting 1. We have 1 minus 1/2 minus 1. We have -1 minus 1/2 and plus 1. Let's see if we got this right. So I get this to be 1/2. 2 minus 1 minus another 1/2, so that is 1/2. 1 minus 1 is 0, subtract another 1/2, so minus 1/2, and another -1/2. So that seems right, and my notes agree. So again, we see that we just have halves for all the elements. So the length of V3 perpendicular is 1, right? But formally, we have that Q3, right? It's 1 over the length of V3 perpendicular multiplied by V3 perpendicular, right? So that's what we want to use, but this here is 1, right? Which means that that 1 ends up here, right? So we have all of R, and we have the final Q3 vector for our Q matrix. Right. So what we should have is that Q is orthogonal, right? So all the columns are definitely length 1, and then when we compute dot products of the columns, we should get 0. Right. So since all the elements have the same magnitude, if we have an equal number of elements with plus signs and minus signs, we get 0. So actually we can check. So we take the first two columns, we generate a plus sign from this minus, minus, and plus, right? So that dot product must be 0. First and the third, we have a plus, plus, minus, and minus. So those two are orthogonal. And for Q2 and Q3, we have a plus, a minus, a plus, and a minus, right? So we will definitely have orthogonality, right? So that's kind of a nice way to check in the end that we did the right thing. So I think we got it all right, so we're off to a good start. So that's the end of that problem. So we need some erase action here. We need the invention of the fast erase. This takes a little bit of time.
Could you explain
Uh, yeah, so I got a question here regarding the length of the vectors. So let's just erase this and then we'll address that question. So for the perpendicular vectors, we got all the elements to be either plus or minus a half, right? So then when you compute the length, right, the square of each one of those components is going to give you a quarter, right? And there are 4 of them, so you sum those up, you get 1, and the length is the square root of that sum, so all those lengths are 1. Yeah, so it sort of formally you have to square all the elements and sum them up and then take the square root. Oh, okay. So you were not a ghost voice because you didn't push the button.
Sure.
So the audience thinks I'm answering a question that was not asked. But no, I promise, somebody is talking in this room, but it may not be recorded. Okay. So let's move on. Next problem on deck is 5.2.31. And what do we have? We have kind of the same problem, right? But we have general vectors. They not only live in R3, so life is a little easier, but the first vector is A, 0, 0. Second vector is BC, 0. And the third vector is DEF. Right, and at the minimum we need to assume that none of these vectors are all zeros. Right, so there's at least some non-zero component to each one. And we just want to run the Gram-Schmidt process on this again. So we will end up with a Q matrix, which is 3 by 3. Right, so we end up with 3 Q vectors of length 3. And we will end up with an R matrix that is also 3 by 3. And that still fits on the screen, just barely. Right, and R is always upper triangular, right? So we can fill in the zeros. Okay, so let's start out. I don't think we have any other assumptions on the coefficients. So the first thing we need is the length of V1. Right, so formally, of course, that's a squared plus 0 squared plus 0 squared and the square root of that. Right, so that gives us the absolute value of A. I think, let me just see what the problem says. We can make our life a little bit easier. Actually, it says that A, C, and F are supposed to be positive constants. So we can assume that, right? So A is actually positive, so the absolute value of A is just A. Right, so we don't have to carry the absolute value around. Okay, so as before, we have lengths. They will show up as diagonal elements over here. Right, so we have our first entry in R, and Q1, first column in Q, is the length of V1 times V1. Right, so that gives us the first standard vector, 1, 0, 0. Okay, so we're done with V1. Then we want to find V2 perpendicular. All right, so usual setup. That is the original V2 then we subtract V2 dotted with Q1, put in the Q1 direction. Now the dot product V2 Q1 is very friendly, right? So what pops out is, well, we have 2 zeros for the last 2 components and we have a 1 in the first component. So we're just going to get B, right? And again, dot products along the way end up above the diagonal in R, right? So we are over here now. So now we can compute this. So we have the original BC0 vector. We are subtracting B times Q1, which is 1, 0, 0. Right, and we end up with the vector 0, C0. And we also had the fact that C is positive, right? So we know this. So this is from the problem. I did not copy that on my slide, but it is in the book. Okay, so we need the usual, right? We need the length of V2, or V2 perpendicular, because Q2 is 1 over the length of V2 perpendicular times V2 perpendicular, right? So again, we only have one entry in here, right? So the length of V2 perpendicular, so formally, right, it is 0 squared plus C squared plus 0 squared and the square root of that. So it's the absolute value of C, but C is positive, so it's just C, right? So again, we have computed a length. I'm going to try to keep my color coding the same, right? So that ends up on the diagonal. And then we get Q2 by dividing our V2 vector by this, right? So we used to end up with a 0, 1, 0 vector. So that's our Q2. We started to see a nice pattern here, right? I think we have enough space to finish the problem over here. So we pick the third vector, and we want to compute V3 perpendicular, right? Which of course is V3 subtract V3 dotted with Q1 in the Q1 direction, and subtract V3 dotted with Q2 in the Q2 direction, right? So project V3 onto Q1 and Q2, subtract that. So the dot products are still very friendly, right? So V3 dotted with Q1, we're just going to pick out the first element of the V3 vector, right? So this is D, and we dotted with Q2, we're picking out the second element, right? So we pick out E. So D being a dot product, right? So the 3 tells us that we end up in the third column. The 1 tells us that we're in the first row, right? So we have D. And here we have third column, second row. So that's our E. So then we have V3 minus D times Q1. Actually, V3, it was D, E, F, and we're subtracting E, 0, 1, 0. All right, so we're just canceling out the first 2 components, right? So the vector we're left with is 0, 0, F. So that's V3 perpendicular. All right, so again, Q3 is 1 over the length of V3 perpendicular times V3 perpendicular, right? And as before, we have one more piece of information, is that F is greater than 0, right? So the length here is just F, right? So again, we've computed a length that ends up over there. And then when we normalize V3 perpendicular by dividing through by the length, we get the 0, 0, 1 vector, right? So that is the full story for that problem, right? And if you are given, so in this case, we live in R3, right? And we have 3 vectors, which, they are linearly independent, so they are a basis for R3. So any, orthonormal set of vectors will be a basis there. But here we got the friendliest of them all, right? So these are just the coordinate axes, right? So it's kind of nice. So hopefully that's clear. So let's move on to the next problem. So 5 to 33 next on deck. See if I can do this. Double the speed. That's okay. Yeah, so all these Gram-Schmidt problems, they take a little while, right? Because there's lots of little computations along the way. And you want to make sure you're not, losing a sign or something, because then things go horribly wrong. So 5 to 33. So we are given a matrix. So the matrix is this. First row, we have all ones. Second row, we have 1, minus 1, minus 1, and 1. And the question is to find an orthonormal basis for the kernel. So first off, we have to find the kernel, right? So what do we do? Well, we want to go to the reduced row echelon form of A, right? So here, that's not too terribly bad, right? So we take the first row, so subtract row 1 from row 2, right? And we end up with first row is unchanged. We have 0, minus 2, minus 2, and 0, right? And then divide this row by negative 2, and we end up with the matrix 1, 1, 1, 1, 0, 1, 1, 0, right? So then we are in reduced row echelon form. No, we're not. We're almost there, right? What we have to do is we have to subtract the second row from the first, right? So then we are at 1, 0, 0, 1, 0, 1, 1, 0. That's a reduced row echelon form. Right, so what do we have? Well, we have two leading variables, right? We started out with 4 variables, so that means we have 2 free variables, right? So I think this corresponds to x1 and x2. They are leading, but x3 and x4 corresponding to the third and fourth column are free, right? So we can write x1 as minus x4, right? And we can write x2 as negative x3, right? And then we play the usual game, right? So we introduce parameters, right? So parameterize, so x3 is s, x4 is t, and we can write our full vector solution, x1, x2, x3, and x4 as the parameter s multiplying a vector, right? So s is x3, so we have a 1 here, and x2 is negative x3, so negative s. x1 does not depend on x3, right? And x4 does not depend on that either. Right, so that's 1. Then we have one more vector. So that is x4, right? And x3 does not depend on x4, x2 does not depend on x4, but x1 does, and we have a minus sign there. Okay. So now we have a basis for the kernel, right? So a basis for the kernel of A is not given by these 2 vectors. So let's not change any signs magically. So 0, negative 1, 1, 0, and minus 1, 0, 0, 1. All right, so we're partway there. Now, what we want, so let's have a little wish list here. We want an orthonormal basis for the kernel of A. All right, so we have a basis, but it's not orthonormal yet. So we have to make it orthonormal. Right, so let's get rid of this stuff that we used to find the kernel. So what do we need to do? Well, we have to take the basis vectors we have, and we have to run them through the Gram-Schmidt process, right, to make them all length 1 and orthogonal. Right, so there was no explicit sort of ask for Gram-Schmidt, but it's hidden in there since we're looking for an orthonormal basis. Now, this problem is quite friendly, because if we look at the given vectors, they're already orthogonal, right? And we can see that if we take the dot product, right, the 0 from the first basis vector will multiply something in the second, but if we have something non-zero in the first vector, that will hit the 0 from the second one, right? So let's call these vectors v1 and v2, and v1 dot v2, right, is 0 times negative 1 minus 1 times 0 plus 1 times 0 plus 0 times 1, which is 0, right? So that means that they're already orthogonal, right? So all we have to do is make them length 1. All right, so the length of v1 is 0 squared plus minus 1 squared, 1 squared, 0 squared, square root of that, so it's the square root of 2. And the length of V2 should be the same, right? So -1 squared, 0 squared, 0 squared, and it's a 1. There's some glare over there, right? So square root of 2, right? So that means that this basis that we're after, we can just take the old vectors and divide by their length, right? So we have 1 over the square root of 2 times 0, -1, 1, 0, and 1 over square root of 2 times -1, 0, 0, 1. All right, and if we, I think we're happy with that, right? So that answers the question, right? So we got a little bit of help, right? So we didn't have to go through the full Gram-Schmidt because we were already orthogonal. If we were not, we would just play the usual game. Okay.
So is it possible for the two vectors to have different lengths? Is it just that it just happened to be square root of 2 for both of them on this one?
Yeah, so the vectors can in general here have different lengths when things pop out. So if we modify this block out here, we can basically get these vectors to be anything we want, right? So it was just kind of, I don't know, luck that they happen to be the same length this time. Okay, let's move on to 35. So 5, 2, 35. And are we getting tired of Gram-Schmidt yet? You can never have too much Gram-Schmidt. I would say that Gram-Schmidt has an extremely high probability of showing up on midterm 3 and the final. And when I say extremely high probability, that probability is close to 1. So we probably cannot do too many of these problems, right? And I like to point out that we're not necessarily just doing this to torture students. Sometimes it seems like it, but the whole Gram-Schmidt process in computing an orthonormal basis is extremely useful for all kinds of problems, right? Because once we have an orthogonal basis, it's very easy to describe projections and all kinds of operations in that basis, and in a way that is not just sort of easy because of orthogonality, but it's computationally good when you start doing things on a computer. Okay, so we are at 5, 2, 35. 5, 2, 35. We are given a matrix, so it's a 3 by 3 matrix. The entries are 1, 2, 2, 2, 1, -2, 1, 1, and 0. And what is the question? The question is find an orthonormal basis for the image of this matrix. So find ortho. If I can't read it myself, then it's bad, right? Orthonormal basis of the image of A. All right. So we're looking for an orthonormal description of all linear combinations of the columns. All right, and that is what the QR factorization gives us, right? So we're just going to start the Gram-Schmidt process on this, and if the vectors, so we have a 3x3 case, if the column vectors are linearly independent, we will find 3 Q vectors that will span all of space. But if they're not, at some point the Gram-Schmidt process will break down, and that will happen here, and we'll see what I mean by breaking down, right? So we just kick this off, right? So we have our V1, V2, and V3 columns. So standard game, right? So we're going to get a matrix R, which is 3x3. And we're going to get a Q matrix. I'm pushing the boundary there, but I think that works, which is also 3x3. Okay, so first thing we need is the length of V1, so the first column. So that is 1 squared plus 2 squared plus 2 squared. All right, so that is the square root of 9. So the length is 3. All right, so again, we have computed a length which ends up on the diagonal. And Q1 is just the length of V1, or 1 over the length of V1 into V1, right? So that gives us, just divide all the entries by 3, so 1/3, 2/3, and 2/3. So let's put that over here for bookkeeping. Then we take the second column, right? And what we want, of course, is the orthogonal components of V2 perpendicular, which as usual is given by V2 minus V2 dotted with Q1 put in the Q1 direction. So we need the dot product. So it's not super friendly anymore, not lots of zeros. So let's do it. So we have the 2 from V2. We have 1/3 from Q1. We have 1 from V2. We have 2/3 from Q1. And we're subtracting 2 from V2 times 2/3 from Q1. Okay. So 2/3 plus 2/3, right, minus 2 times 2/3. That looks suspiciously like a 0, right? So the vectors are already orthogonal, right? So again, dot products end up over here, right? So we get a 0, which makes our life a little easier. And then all we have to do to get Q2, of course, is to take the length of W2 or V2 perp. And since this dot product was 0, well, that is just V2. So we need the length of V2. Right. So this is, of course, 2 squared plus 1 squared plus negative 2 squared, square root of that. So it looks very familiar, square root of 9, which is 3. Right, so this 3 here ends up on the diagonal. And Q2 becomes V2 divided by 3. So we have 2/3, 1/3, and negative 2/3. so far so good. We're starting to feel pretty good about this. Like, the more we practice, the better we get at it, right? The process is always the same. Okay, then we take the third vector, so we can clean this up so I don't have to stand on my knees and use the bottom of the board. I need like a platform here that can go up or down, so you can use the whole board. So short people can use the top and tall people can use the bottom of the board. That comes in the next version of this room. There we go. Okay, so we need the usual, right? We're just running Gram-Schmidt, so we need V3 perpendicular. All right, so V3 subtract V3 projected onto Q1 and subtract V3 projected onto Q2. So we have to compute dot products as usual, right? So we have V3 sitting over here. So we have 1 times the first component in Q1, which is a third. And we have 1 times the second component of Q1, which is 2/3. And then we have 0 times 2/3. All right, so we have 1/3 plus 2/3 looks suspiciously like 1. Okay, so we have a dot product, and it ends up over here. Okay, we have the second dot product. Let's do it up here. So again, we have 1 from V3. We have 2/3 from Q2. We have 1 from V3. We have 1/3. Then we have 0 times negative 2/3. So we have 2/3 plus 1/3. So that is also 1. Okay. Nothing strange has happened yet. So let's compute what we get. We have our original vector 1, 1, 0. We are subtracting the dot product, which was 1 times Q1. So that is 1/3, 2/3, 2/3. We are subtracting this dot product, which is also 1 times Q2. So you subtract Q2. So 2/3, 1/3, and negative 2/3. So if you compute that, first component we have 1 minus 1/3 minus 2/3, 0. 1 minus 2/3 minus 1/3, 0. 0 minus 2/3 minus minus 2/3, 0. That's strange, right? I don't know if it's strange, but it's different. All right, so what that means is that it's possible to write the third column as a linear combination of the first two. Right, so these columns are not linearly independent, right? And we can actually see that. So say we add the first two columns, right? We can then get 3, 3, 0, right? And then divide that vector by 3, then we would have 1, 1, 0, right? So a third times the first plus a third times the second would generate the third, right? So the way that shows up in Gram-Schmidt is that we end up with a 0 vector, right? So this here means we have linear dependence. right? So to answer the original question, right, so let's do that first. So the answer is that, so the question is here, right? So find the orthonormal basis of the image. So that basis is the collection of vectors, right? So 1/3, 2/3, and 2/3. And this one, 2/3, 1/3, and minus 2/3. Right, so that is the answer to the original question. Right. So since we found two of them, that means, of course, that the rank of the matrix is 2. Right, and we have that the dimension of the image of the matrix is 2. Right, these two should always be the same. Right. Now, say you wanted to find the QR factorization here. Right? What do you think you should do? So this is sort of formally our V3 perpendicular, right? So of course, the length of V3 perpendicular is 0, right? So we take that 0 and put it over here. We're fine. Right? But the next step is this, all right? Take that length, divide by it, and multiply, right? So then sort of we get this vector, right, where the elements are 0 over 0. All right? And that's not a good thing, right? So that doesn't work. Right, so we can fill this in, but we need to pick something else. Now, if we think about what the QR factorization does, right? So it says that A is Q times R, right? So we're building the columns of A as linear combinations of the columns of Q, and we have the coefficients in here, right? So in particular, the third column of A, right, we're building from the first column of Q, second column of Q, and 0 times the third column of Q. So we can put anything in here, right? And it will still reconstruct A, right? So we can complete this QR factorization if we want to, and find a Q3 vector which is orthogonal to Q1 and Q2. So the problem is not asking for that, but we could do that for fun, but let's sweep that fun under the rug for now. So we have more problems to solve, but I just kind of want to point to that sort of future possibility. Okay. So the next problem is 5.239. We're spending a lot of time in 5.2. It's like our favorite section in the book, it seems like. Is it a dream or is it a nightmare? I don't know. Right. But hopefully it all makes sense once we've seen a lot of problems here. There we go. 5, 2, 39. We are given what? We want to find an orthonormal basis. So find an orthonormal basis such that the span, we use the same notation here, of U1 is the span of the vector 1, 2, 3, and the span of, actually let's call this Q1. I changed my mind. Q1 and Q2 should be the span of 1, 2, 3, and 1, 1 minus 1. Right. So it's a slightly different question. So we're looking for an orthonormal basis of R3, so that the first basis vector is in the same span as the 1, 2, 3 vector. The second, if we have the span of the two vectors, then we should be in the span of this plane. So it looks like a different question, but it's the same question, right? So what we have is this defines a vector v1, which is 1, 2, 3. And here we have our vector v2, which is 1, 1, negative 1. Right? And let's just refresh our memory what the span means. Well, the span is all the collection of all linear combinations of the vectors, right? So that means like all scalings of Q1 should be all the scalings of V1, right? So we just want Q1 to be the normalized version of V1, right? So Q1 is simply the length of V1 times V1. That's all we need, right? So what is the length? Well, 1 squared plus 2 squared plus 3 squared. So 9 plus 4 plus 1, so 14. Square root of 14. Maybe not the prettiest number in the universe. So our Q1 vector is just 1 over square root of 14 times 1, 2, 3. So that's our Q1. Okay. Then for our Q2, well, we're going to play the usual game, right? So we take our V2. We want to find the part of V2 that's perpendicular to Q1, right? So V2, subtract V2 dotted Q1 in the Q1 direction. Okay. So we have to compute this dot product, right? So we have the entries in V2, right? So they are 1, 1, negative 1. So let's just pull out the 1 over square root of 14, right? And then we just have 1 times 1 plus 1 times 2 minus 1 times 3. And 1 plus 2 minus 3 equals 0. Right, so that is just V2. Right, so they were already orthogonal. Right, now you're like, okay, dot product, right, 1 times 1 plus 2 times 1 is 3, then subtract 3. So yes, they were orthogonal, right? So V1 was orthogonal to V2. Right? So we have the orthogonal piece of V2, which was the whole thing. So the Q2 vector is then just 1 over the length of V2 perpendicular times V2 perpendicular. So what is the length of V2? Right, it's 1 squared plus 1 squared plus negative 1 squared. Right, so square root of 3. So that means that Q2 is 1 over the square root of 3 times 1, 1, negative 1. Right? So we have Q1 and Q2 so that we're spanning the same plane here. Now the question asked for a basis, so the question is this, right? So find Q1, Q2, Q3, right? So that, yeah, we're satisfying this, but all three should be a basis for R3, right? That should be an orthonormal basis, right? So we have two of them. But we have no more information, right? So what are we going to do? Well, we have to manufacture more information, right? So what do we know about Q3? Well, Q3, right, it should be perpendicular to the span of Q1 and Q2, right? It should be orthogonal, right? That means that we can express it as the kernel of a matrix. So let's erase this part where we found Q1 and Q2, and we now have to find the kernel of a matrix along the way. Let the fun begin. It would have been clever not to erase Q1 and Q2, but minor details. But actually that's okay, right? Because whatever is orthogonal to the span of Q2 and Q3, or Q1 and Q2, means that Q3 must also be orthogonal to the span of V1 and V2, right? Because these two spaces are the same. So if we want something that's orthogonal to those two vectors, right, what can we do? We can set up a matrix where those vectors are rows, right? And we're looking for another vector, x, y, z, right, where we just get the zero vector over here, right, 0, 0, right, because if we can solve this problem, that x, y, z vector, the dot product would, each one of the rows is 0, so it's orthogonal with respect to v1 and v2. Right, so we just have to find the kernel of this matrix, so call this matrix M. Right, so that gives us a vector that's orthogonal to the span of these two vectors. So that's what we want to do. So how do we find the kernel? Like, we have to just do what we always do, right? Let's not forget our old stuff. So we compute the reduced row echelon form, right? So subtract the first row from the second. So then we're at 1, 2, 3. We generate a 0, minus 1, minus 4. Divide by negative 1. Right, so we get a leading 1. So we have 1, 2, 3, 0, 1, 4. Then we subtract the twice the second row from the first. And we are in reduced row echelon form. So we have a 1, 0. We're subtracting 8, right? So that should be 5, 0, 1, 4. We are subtracting, so that should be negative. So far my notes agree. So we have two leading variables, right? And we have one free variable, like so x3 is free, right? So usual game, introduce a parameter, and we can write the solution x1, x2, x3 in terms of the parameter. Right. So of course x3 is s, and x1 is 5x3 or 5s, and x2 is negative 4s. Right. So we have a new vector, right, which is orthogonal to the 1, 2, 3 and 1, 1, negative 1 vectors, right? So the span of, so let's call this one V3, right? So by construction, if we erase this stuff, we have three vectors, V1, V2, V3. They form a basis for R3, right? Now all we need to do is to take the V3 vector and make it length 1 and add it to our Q collection, right? So Q3 will be the length of V3, is V3, right? So that length is 5 squared plus 4 squared plus 1 squared. So it's 25, 16, 1. Is that anything friendly? Not really. 42. Yeah, not very friendly. So 1 over square root of 42 times 5, negative 4, 1. That is our Q3. Next, so together with the Q1 and Q2 vectors that went missing along the way, we have our basis, right? So the ortho basis for R3 is the collection then. Fortunately, they're still in my notes. Right, so the first one was 1 over square root of 14. Right, 1, 2, 3. Second one, we had 1 over square root of 3. Oh yeah, that was not too bad. 1, 1, negative 1. And then our fourth one, I can't count anymore, our third one. 1 over square root of 42, 5, negative 4, and 1. All right, so that's the basis for R3 that we're looking for. All right, and the first two basis vectors satisfy that. The first one spans the same space as the 1, 2, 3 vector, and the first two span the same plane as the 1, 2, 3, and 1, 1, negative 1 vector. Check, right? So this problem has a little bit of Gram-Schmidt action in it and a little bit of finding the kernel action, and it all has to be put together. All right, so it's not too bad once you identify what pieces you need to put together. Okay, I think that's the last problem from 5.2. We still have some time, so we will push ahead and move into 5.3 and maybe do something that's not a Gram-Schmidt process. Maybe let's not get our hopes up too much, because all of chapter 5 has something to do with orthogonality, right? There we go. Okay. Well, if this math thing doesn't work out, I can become a window washer. Okay. So, 531. 531. We are given a matrix A, and it looks like this. So entries are 0.6, 0.8, 0.8, and 0.6. And the question is this matrix orthogonal? All right, so what does it mean for a matrix to be orthogonal? We should have that the columns, I'll call them V1 and V2, the columns should be length 1, so we need length of V1 be 1, length of V2 should be 1, and we should have that they are orthogonal, right? So V1 dotted with V2 should be 0. Right? So that's what we're checking. Now, the lengths, right, that's 0.6 squared plus 0.8 squared, squared of that, right? So 0.36 plus 0.64, so 1.00 square root, so that's 1. Right, then of course, if we change this to a 2, we're just flipping the order, right? So both lengths are indeed 1, right? So that's check, check. What about the dot product? We have 0.6 times 0.8 plus 0.8 times 0.6. It seems unlikely that two positive values will cancel out and give us 0, right? It's not that late yet, right? So it's 0.48 plus 0.48, which is certainly not 0, right? So the answer is no. A is not orthogonal. Right, since V1 dot V2 is not 0. Okay, so that means that the vectors V1 and V2 they're not an orthonormal basis for R2 or anything like that. Okay, that's a good warm-up problem. Then we move on to 532. And if you blink, you miss it. It's almost the same matrix. All right, so let's just do a little bit of microsurgery here. The entries are very similar. right? So what are the entries? I said they're similar, so, but they have all moved around, so I guess we'll do some cleaning to stay consistent with what the question is. So we have an entry that is negative 0.8, where 0.6, 0.6, and 0.8. Okay, so what do we have here? Well, the question is the same. Is this matrix orthogonal, right? And again, the length of V1 and V2, right, they are 0.6 squared plus 0.8 squared, which is 1. And now when we compute the dot product, V1 dotted with V2, we have the negative 0.8 hitting positive 0.6. We're adding positive 0.6 times positive 0.8, so we get 0, right? So indeed, we have two vectors that are both length 1 and they're orthogonal, so we have an orthogonal matrix. So let's fill in the 2 here, right? So yes, A is orthogonal. Okay, those are warm-up problems. So then let's talk about properties. So we are at 535 and 536. We are given some matrices that are orthogonal, and then we start combining them and changing them around, and we're wondering what happens to the properties, which means that we have to think about what does an orthogonal matrix do. So let's see here. We are at 535. So we are given a matrix A, which is n by n, and we have a matrix B, which is n by n. So both are orthogonal. So for part A, or part 5, so for this one, we're forming the new matrix C, which is 3 times A, and the question is the new matrix orthogonal? And so a property of an orthogonal matrix is that if you take a vector x, right, and you multiply it by A, then the length is preserved. Right, so an orthogonal matrix, when used as a linear transformation, is length preserving. So then we think about the linear transformation given by C. Right, well, that is 3 times A times x. Right, and then we take the length of that. Well, we're just multiplying by a constant, so that is 3 times A times x equals to the length of x. Don't lose the 3, run into big trouble, right? So when we use the C matrix as a linear combination, we're extending the length of the vector by a factor of 3, right? So it is not, so Lx is not length preserving, which means that the matrix 3A is not orthogonal. Right, so no. Then 5, 3, 6. The matrix we're forming, our new matrix is D. Is just take the matrix B and flip the sign. All right, so then consider the linear transformation we get by multiplying D times X. Well, it's minus B times X. So if we take the length of that, right, then we pull out the constant, the absolute value of -1 times bx, right? This is length preserving. This pen is gone. Right? So b is length preserving because b is orthogonal. So we have the absolute value of 1, which better be 1, and this is just the length of x. So we have the length of x. Right? So flipping the sign changes nothing. Right? So we are length preserving, and therefore we are orthogonal. Right? So yes, minus b is orthogonal. Right? So we're just flipping the sign of everything. We have a bunch more problems like this. I think we can probably do all of them. So we still have our A and B matrices that are both orthogonal. We have added a little bit more information. So not only are they orthogonal, but let's see. Hold on. The A matrix is symmetric, so A transpose equals to A, and the B matrix is invertible, so B inverse exists. So let's write that down. So further, we have that A equals to A transpose, so it's symmetric. And B inverse exists, as B is invertible. Okay. Is B also symmetric? Yes, both of them are symmetric. Thank you. The voices in the room are keeping me straight. Actually, they're not orthogonal, because that's not part of this question, because the question really deals with symmetry, right? So we can actually get rid of, you can tell it's almost time for coffee, right? Minor disasters are happening. So that's where we are. And the question is now 5, 3, 13. We form a new matrix C, which is 3A. And the question is C symmetric? All right, so this is all about symmetry, right? So we have the matrix 3A transpose, and we have a rule, right, saying, well, if you scale a matrix and take this transpose, or you take the transpose and scale it, it's the same thing. So this is 3 A times transpose, and A transpose is A. Right, so what do we have here? We have C transpose, here we have C, and of course they're equal, right? So the answer is yes, C is symmetric. Right, so multiplying a matrix by a scalar quantity doesn't change the symmetry property. Okay. Let's see. I think I can squeeze the next one in before I erase. So we have 5, 3, 15. We are forming a new matrix, call it D, which is A times B. And we're wondering, is that matrix symmetric? All right, so we have D transpose, which is AB transpose. All right, then we have the transpose rules. Right, so the transpose of products of matrices are the products of the transpose matrices, but in the opposite order, right? So it's B transpose, A transpose, right? But then we use the fact that both A and B are symmetric, right? So in this case, that is B times A, right? However, so the question is that equal to D? Right? So question, is that equal to A times B? Right? In general, the answer is no. Right? So in general, A times B is not equal to B times A. Right? Because matrix multiplication is not commutative. Right? So matrix multiplication is not commutative. Right, so what matters? So the answer is then no, right? So this matrix is not guaranteed to be symmetric. So let's change the color here. So not guaranteed to be symmetric. Right? So it could be, but it's not necessarily true, right? I mean, A and B could both be the identity matrix, right? And in that case, it is symmetric, but you cannot guarantee that that's the case. Let's see. I want to squeeze in 2 more problems using the same matrices, and then I think it's time for a break. Right, so more properties of the transpose. There we go. So we have 5, 3, 17, and we're forming the matrix, call it F, which is B inverse. And again, the question is that symmetric? Right, so F transpose is B inverse transpose. Right, then one of the properties is that we can change the order of the transpose and the inverse. Right, so this is B transpose inverse. All right, so that's a property of matrix operations. Then we have the property of the matrix itself, right? So B is symmetric, so B transpose is B. So this is B inverse, right? So that says that when we started with B inverse, we took the transpose, we got it back, right? So that is F. So in this case, the answer is yes, right? So if B is symmetric, then we must have that B inverse is symmetric. Then we have 5, 3, 19. We are forming a matrix, call it G, which is 2 times identity of the appropriate size. All right, so used an n by n matrix with ones on the diagonal. To that we add 3 times A, and we subtract 4 times A squared. And the question is G transpose symmetric? All right, so write out what G transpose is. All right, so it's 2 times identity plus 3A minus 4A squared. And we transpose that. So the rule for sums of matrices is that we just take the transposes of the various pieces and add them up, right? So we have 2 times the identity matrix transposed plus 3A transpose minus 4. And I'm just going to write A squared as A times A, because why not? Then we know that we can multiply by a constant and just pull it out. That doesn't change the symmetry properties, right? That's from part 13, right? So we can write this as 2 times identity transpose plus 3 times A transpose minus 4 A times A transpose. So what do we know? Well, identity is a diagonal matrix, right? So if we take a transpose of identity, we get identity back. So this is just 2 times IN. We have 3 times A transpose, but A transpose equals to A from the property of A, right? So that's 3A. Then we have minus 4, right? And we have A transpose times A transpose, right? So the A's changed places, right? So this A went over here, that A went over here, right? It changed the order. Well, they look the same, right? So who can tell? But again, we use the fact that A is equals to A transpose, right? So both of these are A's, and we sit at 2 times identity plus 3A minus 4A squared, which is the original G that we had, right? So we have shown that G transpose equals to G, where G was this stuff. So the short answer is yes, that combination of matrices is also symmetric. So I think that's a good place to call it a day. My brain cells are running a lot slower than they did in the beginning. So thank you guys.